Hello, my name is Taylor Baugher, and this is Lab 5, the Falling Slinky. There are three purposes to this lab. The first is to observe and track the motion of the bottom of a slinky falling from a known height. The second is to model the object falling with air resistance from the same height. The third purpose is to analyze and compare the experimental and observed models. Before we begin, I'm going to introduce you to a few formulas and laws that we will use in order to complete this experiment. First, we have Newton's first law, which states that an object in motion stays in motion unless a force acts upon it, also known as inertia. Second, we have the momentum principle, where F net is equal to the derivative of momentum. Third, we have velocity and position update formulas. Now let's look at our experimental model. To set up the experimental model, I used the height of one of the people to calibrate the video. Then, I set the FPS to 300, which was stated in the original video. I also set the origin to be the bottom of the slinky, and the slinky's mass was 0.218 kilograms. We tracked the point of mass as the bottom of the slinky and saw how it moved as time versus the y position, and then we plotted that. The system is the slinky and everything else is the surrounding. Our results from the experimental model show that in the first portion, y position does not change. This is because tension and gravity are working in equal and opposite directions, so F net is equal to 0. Then in the downward portion, we can see that the y position is decreasing. This shows that there is not a constant velocity, and therefore there is an acceleration of net forces not equal to 0 in the second half. Therefore, there must be drag or air resistance. Now let's look at our computational model. When setting up the code for the computational model, we use the same initial conditions from the experimental model. This is to eliminate any inconsistencies between the two. Also, we found our drag constant 2.085 through trial and error. For the first while loop, we use the time found in the first experimental model from when the slinky stays at rest, and we calculate the force of gravity and tension and add those together to get F net. Then we apply the momentum principle using the object's velocity and position to update to its new velocity and positions. The second part of the code, we used the entire time that it took for the slinky to fall to the ground. Then from here we used the same formulas where we calculate net force, but this time there is no tension and it's just the force of drag and the force of gravity. Then we plot our y versus time. The results of the computational model show similar results from the experimental model. We see how the y position stays the same until the top of the spring reaches the bottom of the spring. This means that there is an acceleration in the second half, and F net does not equal 0 in this same part. When we compare the two time versus y position graphs, we see that we got similar results, and they match up pretty closely. There is going to be some error in tracker due to human eye tracking, and the air resistance was also calculated through trial and error for the modeled experiment, so this could cause some difference. There was also an issue with timing due to a slowed down version of the tracker video.